Hello, hello. Hey, hello, Asad.
Hello, ma'am.
Is your internet okay now?
Ma'am, it's still a little frisky, but I can understand what you're saying right now better than before.
Okay, Asad, you remember that in one of the last classes we discussed that you will be working on the harmonic oscillator. In fact, you wanted to do this, right?
Ma'am, I was proposing that if you would have some problem with my topic relating to the effect of trapping, then I would be working for the harmonic oscillator.
Yeah, I think you should go ahead with it because there was another student who had to drop this topic because you were interested. So I would like you to go with this, with the harmonic oscillator. Okay?
So you're suggesting that I should go for the harmonic oscillator rather than the effect of trapping?
Yeah.
All right, ma'am.
Yeah, so please, since you guys have not done this topic as a part of the course, I would like you to explain this in detail. Okay?
All right, ma'am. Noted.
Okay, good. And Isha, how are you?
Yes, ma'am. I'm good, ma'am. Thank you.
Okay, have you submitted your assignment?
No, ma'am, I haven't, but I will in short time.
Okay, anyway, but your topic was finalized, so you can continue working on that, right?
Yes, my topic was scattering, and I am gonna specify it in electromagnetic scattering or
Okay.
neutron. That I haven't.
Yeah,
Yes.
you have this topic in the quantum mechanics book. You have it in Griffith, you
Yes.
have it in Lebov, so you can use
Yes.
material. Yeah. So it's a,
Right. Right, ma'am.
yeah, so it should be at the level of these discussions that we have in the book, right?
Right, ma'am.
Okay, good. Okay, so let's continue. So, so since we have been working with the operator Lz and we've also worked with the operator L squared, now we can find their simultaneous eigenvalues, right? And eigenfunctions. So the simultaneous the simultaneous eigenvalues and eigenfunctions of Lz and L squared. Now these two operators commute.
Ma'am, we can't see your screen.
I didn't share my screen. Okay. Um, okay. Now you can see it, right?
Yes, ma'am.
Yes, ma'am, we can.
Yeah. Okay, good. So you can see that we were working with the LZ operator last time, right? So we have that expression. This time we worked with the L squared operator. We have these expressions, and now we can find their simultaneous eigenvalues and simultaneous eigenfunctions, just like we did in this last part of the meeting, right? We did it for LZ, and now we're going to do it for these two operators. And these two operators commute. So it is possible to find the simultaneous eigenfunctions and eigenvalues. So let us again start with psi, and let us assume that this is the simultaneous eigenfunction for Lz and L squared. So let the eigenvalue of L squared be C, and that of Lz be mh bar, where m has the values 0, plus minus 1, plus minus 2, and so on. So the eigenvalue equations corresponding to the operators Lz and L squared are Lz psi equal to mh bar psi and L squared psi is equal to C psi. So we get these two equations. Okay, so now let us consider an operator which can be written as, are you familiar with this operator? Yes? No?
I think, ma'am, we've done this. I think close to it in electrodynamics. I think if it's
No,
that
we did
one,
it in quantum
otherwise
one,
no.
I think.
So what is it
Or
called?
transpose or adjoint, either of these.
No, this is not a transpose and it's not a joint. What is it? Yes? This is called a ladder up operator. Okay? Okay. So let us pre-operate equation 1 by this operator. And we get is equal to mh bar, and then this operator applied on the function psi, and we get equation number 3. This is equation number 3. So now we can actually apply it into LZ. So this should be equal to, when we open this, and let us call this equation number 3a. Now, using the fact that this expression is equal to iota h bar LZ, we can say that Ly LZ minus LZ Ly is equal to iota h bar Lx. And similarly, Lz Lx minus Lx Lz is equal to iota h bar Ly. So putting these values, of Lx Lz and Ly Lz in the equation 3a, we get what? This operator applied on Lz will be equal to. Now I would like you to do this actually. I've given you all the expressions and the values, and you just have to plug them in, right? ठीक है?
Yes, ma'am.
So please do that.
Yes, ma'am.
You can plug this here. So these are 2-3 steps. So if anyone can tell me, and I can give you a point for this, right? If you can fill in these steps, right? And the final expression that we then arrive at is this should be equal to LZ L plus minus H bar. Okay. ठीक है? Has anyone done this?
Yes, ma'am, I've done it.
Who has done it?
Ma'am, Mahnur.
Manu. Ji Manu, can you help us write it?
Yes, ma'am.
Okay. Let's start with the first one. So let me go here. This one, right? And when you write this, it becomes लिखो बताओ.
Ma'am, it becomes LZ LX minus IH bar LY.
Just a moment. Okay, LZ LX minus iota H bar LY
LY plus
plus
iota multiplied by
iota multiplied by
brackets में iota H bar LX plus
ये
LZ LY.
ठीक है, right. Good. Okay. Just a moment. So, and then
Ma'am, after the expansion, it basically boils down to LZ LX.
just a moment, let me erase this.
Yes, ma'am.
Okay. So we have this is equal to, yes,
Ma'am, LZ LX
yes,
minus iota H bar LY
yeah,
minus H bar LX
yes.
plus iota LZ LY.
Okay. And then the last step,
Ma'am, we take LZ terms common.
okay,
That leaves us with LZ and bracket LX plus iota LY
yes,
and minus H bar, then again a bracket LX plus iota LY.
yes, very good.
Then the operator, the ladder up operator, it gets substituted into the brackets and we get the expression.
Very good, very good. Yeah, so you get a point, right? So we get this expression, right? We can, now let me note this point. Okay, fine. So we get this. And now we can put this value in equation number 3. Another thing you can notice from this expression is, for example, when you look at this, you can rearrange it and you will get what? Well, we don't have to do it for this problem, but for another problem, or just you might need it sometime. You know that you can use this expression, you can rearrange it to write it as something like this. Minus and then you can show that this expression is equal to minus h bar and this letter operator, right? So this is a side note. This is something that can, but we don't exactly need it right now. Okay, so coming back, let us put this value, continuing with what we started. We get in equation number 3. And so you can see that this is a commutation relation. So we could either derive the steps as we did, or we could directly use this commutation relation. So anyway, so putting these values, we get applying it on the function psi, this should be equal to mh bar, ladder up operator applied to the function psi. And then again, we simplify this. We do this here, this one step, and then we do another step. And we finally arrive at Lz L plus psi is equal to m plus 1 h bar and the ladder up operator applied to psi. So this is equation number 4. So equation number 1 tells us that mh bar is the eigenvalue as we started in the beginning, right, of Lz, and corresponding to the eigenfunction psi. And equation 4 tells us that m plus 1 h bar is the eigenvalue of Lz corresponding to the eigenfunction L plus psi. So you can relate these two equations, and you can then explain how these eigenvalues correspond to the eigenfunctions. So we can write this down. Equation 1 tells us that mh bar is the eigenvalue of Lz corresponding to eigenfunction psi, and equation 4 tells us that m plus 1 h bar is the eigenvalue of Lz corresponding to eigenfunction L plus psi. Okay. So similarly, we can show that Lz applied on the function L plus squared psi is equal to m plus 2 h bar L plus squared psi. And let us take equation 2. And pre-operating by the ladder up operator. So we get this expression. This was the value, and this is the function, and we get equation number 5. So we can write this as is equal to Lx plus iota Ly into L squared. This should be equal to Lx L squared plus iota Ly L squared. And since these commute, since Lx L squared and Ly L squared commute, so we can write these above equations. As L squared is equal to L squared Lx plus iota L squared Ly. And then taking this common, we can substitute it with the operator. Again, in this case, we could directly say that since L plus and L squared commute, and therefore we can use this expression, right? We could also say that as we can either do the steps or we can use this fact that they commute, and therefore we can have this is equal to L squared L squared and the ladder of operator. Okay, right. Wow. So putting this value in equation number 5, we get And therefore, we can write this in the form that we were writing before. And this is equal to C into L plus psi. And this is equation number 6. Okay. So equation 2 showed that C is the eigenvalue of L squared, right? Corresponding to the eigenfunction psi. And equation 6 shows that C is the eigenvalue of L squared corresponding to the function L plus psi. Thus the eigenvalue of L squared remains constant. So this is an important conclusion here. So equation 2 shows that C is the eigenvalue of L squared corresponding to eigenfunction psi, and equation 6 shows that C is the eigenvalue of L squared corresponding to L plus psi. So this leads to the conclusion that the eigenvalue of L squared remains constant. ठीक हो गया? Right? So just like we did this time, we can also prove that following a similar procedure, we can prove that L squared applied on this function will be equal to the eigenvalue multiplied by the function. ठीक है? And Asad. So Taha is not in the class at this time, right? Okay, so we can stop here and then we continue from here next time. Okay?
Okay, ma'am.
Right, ma'am.
And you also, of course, work on the topics that you have selected and complete the papers for the next deadline, right?
All right, ma'am.
Okay, okay. Take care.
Take care, ma'am. Allah Hafiz.
Hafiz.